So the wavelength that comes out from this relationship from massive objects which have a mass of the order of 1 kilogram and 1 meters per second is exceedingly small. So this lambda is extremely small on the length scales that we are used to measuring. That's why this effect is not observable in the macroscopic world that we live in which we have heavy objects moving at some speed. Objects which have reasonable momentum lead to a very small wavelength. And the wave nature is not evidently clear in the macroscopic classical world. Now I am preparing a tutorial that will actually bring home this fact in more detail. Now the question is, if I draw a wave of this kind or a wave of this kind, how is it related to the wavelength? How can I define the wavelength for such a wave? Yes. So if you have zero velocity here, the wavelength is going to be infinite. Okay? Which means the object is at rest and the wavelength becomes undefined in this case. Okay. Alright. Now, before we move on, I would just like to give you a qualitative idea of what this object really means. Suppose I have a sine wave of amplitude A1 and phase phi1. Alright? So I can write this wave as A1. Let me write it bigger. I can write this wave as A1 e raised to I K1 x plus phi1. Correct? So this wave has an amplitude A1, phase phi1 and a wave number K1. Correct? I can express this wave in complex notation in this form. There's an amplitude and this is the phase. This is my x-axis. And I'm ignoring time for the time being. So I'm just taking a snapshot of this wave at a fixed point in time. The amplitude is A1, that's just the magnitude of this complex number, and the phase is given by kx. For this wave, k is k1. This is 2 pi over lambda 1. This wave has a precise wavelength, you know that, and it has some phase phi1. So now what I'm going to do is I'm going to draw a sine wave A1 ei k1x plus phi1. This is my x-axis. And now I draw another wave. Which has a different amplitude, a different wavelength, and a different phase. And now I draw a third wave which has a totally different amplitude and a different wavelength and a different phase. I yet draw a large number of waves. All of them are sine waves or cosine waves. Each one of them has a precise wave number, which means a precise wavelength. This k is equal to 2 pi over lambda. So this is 2 pi over lambda 3, this is 2 pi over lambda 2, and so on. I can draw as many waves as I like of differing wavelengths and different phases. Now if I add up all of these waves, I will get a different looking pattern. I will not get a sine wave. I will get a sine wave only when the two waves have the same wavelength and the same phase. They can have different amplitudes, but if this wavelength is different for all the waves, and we have different amplitudes, and we add different proportions of all of these waves. So I add C1 of this wave, I add C2 of this wave, I add C3 of this wave. So I mix these waves, add them linearly, and different proportions of each wave are being picked up. I can construct a wave that looks radically different from a sine wave. Alright? Now, it is also possible to construct something like this. If I choose my coefficients intelligently. Alright, so if I have a wave like this, I can express this as a superposition of component waves of different amplitudes, different wavelengths, and different phases. I can decompose any pattern that I can imagine into sine waves with precise frequency, precise spatial frequencies, wave vectors, precise amplitudes, and precise phases. This process of decomposition is actually called Fourier decomposition. So Fourier theory suggests that if I have a pattern, an arbitrarily looking pattern, I can always decompose this as a sum of sine waves. Alright? So this wave, in fact, this pulse that I've drawn over here, is in fact a superposition of complex numbers, each one of them picked up in different proportions. And these proportions are determined by Fourier theory. I can decompose this pulse and this pulse into its component waves. So this pulse doesn't have a precise wavelength. It is built up of waves of precise wavelengths, and we pick those up in precise proportions. This is called the Fourier decomposition. So it doesn't have one wavelength. It has a whole baggage of wavelengths associated. Okay? And all right. Yes. Complex may be confused. Complex is a sum of sine and cosine. Yes. I mean, you have to pick up these. If you want to. Alright. So if I want to make a pulse of this kind. Okay. So this is x. This is x naught. This is 0. This is minus x naught. Suppose I want to make a pulse of this kind. Then what I need to do is I need to pick up wavelengths in precise proportion. So what I need to do is the following. Let me first draw the picture, then let me explain what this means. Okay. So this is my x-axis. I'm showing you a result that you will learn later in your life in order to answer this particular question. I want to construct this particular waveform, this wave. Then what I need to do is I need to pick up a sine wave which has a k equal to 0 and this proportion of that sine wave. K equals 0 is just a DC, it's just a straight line. Then I need to pick up a certain value of k, let's call it k1, and the amount I need to pick up is c1, and this is the amount of k1 wave that I need to pick up. So I need to compose sine waves of different values of k and pick up certain amounts of them, and the amount that I need to pick up is given by the vertical axis of this graph. So I need to pick up certain amount of k equals 0, I need to pick up certain amount of k equals 1, a certain amount of k equals 2, a certain amount of k equals 3. I cannot pick up, I don't have to pick up any amount of k which equals this value, which is given by 2 pi over x naught. So I have to be precise in the amounts of different waves I pick up. I cannot arbitrarily pick up certain amounts of this wavelength and certain amounts of this wavelength. If I need a precise waveform in space, I have to do a Fourier decomposition and calculate what amounts I need to pick up. Okay, and this is called, these coefficients are called the Fourier coefficients. Yes. Of course we can do that. So you can always do that. That's not a problem at all. That's in fact what you do in a laboratory. So you have function generators that are putting out different frequencies, and you take and you add up all the components, you will get a different looking waveform. Okay? In other words, if you want to look at this mathematically, what we have is that fx is given by eikx any fx can be built up from taking a sine wave, this is a sine wave, eikx, and multiplying it with a certain constant. That's the amount of this particular wavelength that we picked up, and summing up over all cases. Now this ck is determined in a precise fashion. Okay, the ck is determined by f of x e minus ikx dx. Okay, now I don't want you to remember all of this, but there are precise rules of picking up the ck's. Yes? Are you afraid of it? No, I'll just keep things at your level. Okay, but I will have more to say about this Fourier transform business in the next lecture when I talk about the uncertainty principle. It's very important. It's at the heart of modern quantum mechanics. Don't be afraid. Alright, let's move on. So now with this background on the de Broglie relationship, what I now want to talk about is a famous experiment, which is arguably the most universal experiment that can be done in physics, which teaches you all there is to be taught about quantum mechanics. And that is called the famous double slit experiment. Now what I have in this particular case is the following. I have a light source. This could be a bulb or it could be a laser, something that is emitting light. Here I have a screen which is opaque, but inside this screen there is a slit, S1, here it is. And after a certain distance, there is another opaque screen which carries two slits, S2 and S3. Is the handwriting large enough to see at the back?
No, sir.
Can you please increase the size?
Can I please repeat?
Can you please increase the size?
Alright, I will. Let me just have a look. Alright, now I'll increase the size a little bit. After a certain distance, there is another opaque screen. And some kind of pattern can be seen on this screen. Now if we perform this experiment with light, you've already seen this experiment in your A-levels, it's called the Young's double-slit experiment. What kind of pattern would you observe on the screen? You will see fringes. Alright. Now, if I were to draw the fringes, there are different ways of drawing the fringes. One possibility is that I just draw the fringes themselves. So I have a dark region in which very little light reaches, followed by a bright region, not of uniform intensity, but still brighter than the dark. Then I have interleaved bright and dark regions. So this is the conventional pattern that one would see if one were to perform this experiment with light. Now there's another way of drawing these fringes or representing these fringes, and that's the following. Now this is a distance axis, right? So we moving along the screen when we are moving in the vertical direction, and on this axis, if I were to draw the intensity of light, I'm using this word for the first time, the intensity of light, then these patterns would look like the following. So this is a dark region, this is bright. Dark, bright. Dark, bright. Alright, so this is an alternative representation of the fringes. This is called an interference pattern. Now why are these fringes formed? These fringes are formed because this light is a wave, and waves interfere. So generally we think of what's happening is that there are wave fronts coming out from this light source, and this slit acts as a secondary source of wavelets. Alright, and these two slits act as further secondary wavelet sources, and these waves then interfere. So there are regions where two waves interfere constructively, and there are regions where two waves interfere destructively, and as a result, if we see what's happening on the screen, we get alternate bright and dark fringes. So these interference fringes are a result of the wave nature of light. There's no doubt about it. We perform this experiment all the time in our laboratories. This is what we observe. We will observe this phenomenon with water waves, with any kind of medium wave that we are accustomed to. So this is the intensity pattern corresponding to interference of waves. No doubt about it. In fact, this was one of the earliest experiments that was used to determine the speed of light. And it can also be used to determine the wavelength of light. And you can actually look at the spacing between the fringes and find out what the wavelength of light is. Okay? Now, if we were to perform this experiment with particles, what's going to happen? Suppose instead of a light source, I have some micro bullets, for example, which are classical particles, which are real particles. They're still macroscopic in size, you can look at them, but they're small bullets that are being showered by a special kind of pistol. So these bullets are being showered, and then what's going to happen if you perform this experiment with bullets, then an interference pattern will not appear, because the bullets can't interfere with one another. The bullets either go through slit S2 or through S3. Alright? So now if I were to draw the kind of pattern that we would observe with classical particles, what kind of pattern would we see? We would see a pattern which has a hump here and a pattern which has a hump here. Because if I were to draw the trajectory of a single bullet, this bullet might come off here. It might pass through S1 in this direction, reach S2, and then it can either go straight or it can hit the edges of this screen and be scattered in different kinds of directions. So as a result, you will get a hump of this kind. Likewise, the same could happen on the other side. So corresponding to bullets or particles, you don't get an interference pattern. What you do see is this bimodal distribution. This distribution of bullets in which there are two humps. One corresponding to the slit, the bullet passing through S2, and this hump corresponding to the bullet passing through S3. If I were to put my hand on one of these slits, or if I were to close this slit, what kind of pattern would I observe with bullets? I will just get one hump. And if I were to close this slit, I would get the hump in the other direction. I would get this hump. And if I were to make both slits open, I would get the blue bimodal distribution. If I call this pattern I2, I call this pattern I1, then is the blue pattern just the sum of the two intensities? Yes, it is. It's just I1 plus I2 with some normalization factor, right? So if I have intensities I1 corresponding to slit S2 being closed, I2 corresponding to slit S1 being closed, if I keep both slits open, the pattern that I observe is just a simple sum of the intensities. Correct? For waves, on the other hand, if I were to close one slit, what kind of pattern would I observe? Would I get fringes? No, I will not get fringes. I will get this pattern with one slit closed, and I will get this pattern with the other slit closed. If I were to perform this experiment with a single slit, for example, this is my light source. What kind of pattern would I observe? I will just get a single hump like this. Alright? This is what a shadow, this is just the shadow of the screen. Bigger this slit, sharper will be this hump. But why is the hump spread out? I'll explain this because it's because of the uncertainty. If this slit is big enough, I don't see a hump. I will just get an image of the slit on the other hand. If this slit is small, how small? This width of the slit, D, has to be of the order of the wavelength. I will get a pattern of this kind only if this condition is satisfied. Alright? So with waves, if I close one slit, I get this green hump. If I close the other slit, I get this hump. But when I keep both slits open, the waves interfere and I get an interference pattern. And the interference pattern is not the sum of these individual components. It's totally different. Alright? Now what we would like to do is we would like to enter the quantum realm. We would like to enter the quantum realm. In the quantum realm, we would like to focus our attention on one so-called particle, which is called the electron. Alright? We would like to perform this experiment not with light, but with electrons. And we would like to see what are electrons. So I would like to pose in front of you the basic fundamental question, what is an electron? And I would like to see what's the character of an electron. If I were to perform this experiment with electrons, what's going to happen? This is the question that I put forth for myself. Now, I would like to repeat this experiment not with photons, not with light, but with electrons. So I have the same experimental setup, a slit, followed by an opaque screen with two slits, followed by a screen. My source now is a stream of electrons. Now, how do I produce electrons? How can I get a stream, a beam of electrons? By thermionic emission. I can heat a filament, I can pass a current to a filament, and as current goes through this resistor, it heats up. And if it heats up enough, the temperature goes large enough, electrons will evaporate from inside the metal, they will come to the surface and eject. They will come out. This is what happened in our old television tubes, in our cathode ray tubes. This is how you get a beam of electrons. So now these electrons are coming out and they're going in this general direction with a certain speed, for example. Alright? Now how can you accelerate electrons? By applying an electric field. By making this side positive, this side negative, electrons will be accelerated and they will pick up energy. And the amount of energy an electron picks up is given by E, which is the charge on an electron multiplied by the potential difference, V. This is the amount of energy an electron is going to pick up in a potential difference. So you can accelerate electrons. You can make electron accelerators. Now these electrons are being shoved to our experimental arrangement. Alright, now if you were to perform this experiment with electrons, what we observe is that the electrons are behaving like waves. And de Broglie actually proposed the idea that associated with these so-called particles there are waves. Now if there are waves, then those waves must interfere. And when they interfere, you must get interference patterns in a double-slit experiment. So what we actually observe when we perform this experiment is that we see these interference fringes. And if I were to draw the intensity pattern, this is what it's going to look like. So this is my intensity, I. This is what my visual observation is. I get interference fringes, and if I were to have a mechanism in which I can find out the intensity of the electrons. Now what do I mean by the intensity of the electrons? Repulsion? Alright, let's talk about this in a minute. But first of all, let me look at the question is what is meant by the intensity of electrons? The number of electrons. So what you have is, you're looking at the number of electrons reaching a certain point along this stream and just waiting for some amount of time and seeing how many electrons are built up in that finite width of time. Then you change your position on the screen and wait for the same amount of time and find out the number of electrons reaching here. So you make a histogram in a way. And if you perform your experiment large number of times, you will get an intensity pattern. Alright? Now this is your visual observation. So if you start your experiment and let it run for a certain amount of time and then take a camera, with the help of the camera you image this screen. This is your camera here. This is what you will visually observe. And this is just a profile of this image. This intensity pattern is a profile of this image. This is a quantitative representation of this intensity. This is the visual representation and this is quantitative. Now she's asked the question that these electrons are going to repel one another. Alright, so that factor has to be taken into account. But let's perform this experiment with neutrons. Neutrons are uncharged particles, you'll get the same pattern. So indeed, classically, these electrons are going to repel one another and there will be a dispersion superimposed on top of it because of the repulsion of the electrons. But let's ignore the charge for the time being. Say if I were to perform this experiment with atoms, hydrogen atoms, they're uncharged. With neutrons, you'll get the same interference pattern. So the charge does not change the logic. Okay, it does affect the physical outcome, but it doesn't say that the fringes will disappear. They will still be there. Alright, so far so good. There's no problem about it because these electrons are acting like waves. So if electrons are coming out in this region, they are just acting like waves, matter waves, pilot waves, de Broglie waves, whatever you would like to call them. These are waves. Alright, here there are secondary waves. And then these secondary wavelets interfere to give rise to the interference fringe. So far, so good. Yes. Keep the potential difference, electron charge, energy. So the question here as well. Alright. Now starts the real fun. The excitement starts here. Okay, now this is probably the most important section of our course. It's coming in the very first week of this course. This is the gist of all of quantum mechanics. So you really need to understand this segment of my class. Now what's happening here, these electrons are particles. Alright? So now if the wave is being ejected or issued from both of these slits, where are the electrons? The question is, where are the electrons inside this apparatus? So if there are interference fringes, it means that some electrons are going to this slit and some electrons are going to this slit. And these electrons have a wave-like nature associated with them, and so do these. And these waves then interfere and give you this pattern. Alright? So some of the electrons go to this slit, some of the electrons go to this slit. And there's a bunch of electrons coming in. So there is a bunch of electrons that is coming into the apparatus, all of them together. Some of them move to this slit, some of them move to this slit. By symmetry, half of them go to this slit, half of them go to this slit. Each one of them then has a wave-like character associated with it. Those waves interfere and give you an interference pattern. This is our general description of this experiment. Alright, now let's modify this experiment a little bit. Now what we would like to do is, we would like to reduce the intensity of these electrons. Generally, we have millions of electrons coming out of the electron gun. Large number of them. So there is a possibility that half of them would go to this slit and half of them would go to this slit, because these electrons occur in bunches. There are so many of them. There is a swarm of electrons. And half of them go to one part, the other half go to the other part. And then there is the possibility of interference if you do believe that waves are associated with these particles. Now we would like to modify, crack the handle a little bit by reducing the intensity of the electrons. And we reduce the intensity or attenuate the electrons to such a degree that an electron comes out and then there is a silent period. And then another electron comes out. So we have reduced the intensity of the emission of electrons. The emission of electrons has been slowed down appreciably. So it is only one electron at a time coming out of the same apparatus. So there's one electron, there's a wait period. Another electron, a wait period. And then we have to see what kind of pattern do we observe. So let me give you 1 minute of silence here, just to think of what's going to happen, and then I'm going to explain. It's not a break, it's just 1 minute of silence, careful contemplation inside the class. Alright, before we move on, one question one of the students has asked, why do we need this slit? This slit is just needed for single slit diffraction so that when whatever particles come in, they are spread out in a cone so that both of these slits are seeing particles. If you don't have this slit and there's a beam of electrons coming in, they will not spread out. So you want both of these slits to see particles. Okay? So diffraction is going to occur here and there's going to be a fanning out of the particles. And those particles will then reach both of these slits. You want to make that happen. If you have a laser beam and that laser beam shines on this screen, that laser beam is not going to diverge. It's going to fall straight here and none of the particles will reach these slits. Okay? Now what's going to happen in this experiment? First of all, what do you observe? And how do you observe electrons? You need some detector for seeing electrons. One of the possibility is that you have a plate, a film made up of zinc sulfide. The zinc sulfide is a phosphorescent material, which means that whenever a charged particle hits a certain point in this film, it changes its color. It glows. In the old television sets, there was a greenish glow on the screen. That was due to coating of zinc sulfide. So you need some kind of detector for the electron. And then you have a detector that detects a single electron for this experiment to work. Right? So if an electron comes and falls on a detector, it must give you a certain flash. It must speak up. An electron is a tiny charge. It's the unit of charge. So it's a really small particle with a small charge. So you need some mechanism of converting this small impingent electron's charge into a macroscopic measurable signal that can be observed as a click on a loudspeaker, tick, or a blip on an oscilloscope screen. So you have to convert this single electron into a measurable signal, right? And this is possible these days with single electron detectors. And such detectors, for example, could be avalanche photodiodes. Alright, so we have detectors that detect single electrons. Suppose there are detectors everywhere on this screen. So the detectors can tell whether an electron is reaching that particular point in the screen or not. And these detectors have an address on the screen, so you can tell where the electron is falling on the screen. Now there's one electron at a time. This experiment is different from the former experiment because of this single electron nature. Which means there is one electron at a time precisely through this apparatus. Which means that only one electron is coming in at a time. The emission is so slow, it's one electron at a time, and when the electron has fallen on the screen, the speed is such that after the electron has fallen on the screen, the second electron is issued from the electron gun. So everything is slow and steady. Now if you have detectors all around, the counterintuitive, non-commonsensical, apparently non-commonsensical outcome is that still fringes will be observed. This is totally strange, and I'll explain why. So still, if I were to draw the pattern that is observed, you will never get electrons here. You will always get a higher intensity of electrons here, never here. In other words, you get dark and bright fringes again. And if I were to draw the intensity pattern, alright, still I observe interference fringes, even with a single electron. Now if, alright, there's no problem with that, an electron is behaving like a wave. So that single wave comes in here. But then, if the electron goes to this slit, or so let me ask you the question, what is the electron interfering with? If there is one electron inside this apparatus, the electron is either going to slit S1, S2, or it's going to S3. It's impossible that the electron can be split, because the electron is an indivisible particle. You cannot split up an electron. There's nothing smaller than an electron. You cannot take a knife and cut up an electron into two. So if there are fringes, if there is a wave coming out of this slit and the wave coming out of this slit, it means that the electron is coming out of this slit and it's also coming out of this slit, but this is a contradiction because the electron is indivisible. How can you divide an electron? And it's also not possible that there are two electrons coming into the apparatus, one of them is coming here, one of them is going here, and they are interfering, because there's only one electron in the apparatus. So how do we explain these fringes? It's a totally surprising result. You will get interference pattern even with a single electron, and the question is, where is the electron? Is it actually split? And which path does the electron take? So all of these questions naturally come to our mind. And what is the electron interfering with? Because there is no neighboring electron to interfere with. There's one electron in the apparatus. And an electron can never reach here. What is telling the electron that this is a forbidden region? What is telling the electron that you should never go here? What's in the mind of the electron? Does the electron have a consciousness? What's making this interference pattern? That's the fundamental question. And this was one of the main conundrums which gives spark to a new mode of thinking. It's called quantum thinking. Alright? So I hope you do understand the dilemma that we face here. If we perform the double slit experiment with single electrons, one electron at a time, still we observe interference patterns. So the devil's advocate might come up and say, okay, if you're unsure of what's going to happen, let's see which slit the electron goes to. Alright? So the devil's advocate comes up and he asks a question. He's a lawyer, so he's fond of asking questions and always arguing with the arbiter. So he comes up and asks the question, alright, you can't tell which slit the electron is going through, let's actually find out. So he introduces a spy into the system. And that spy is a reporter that tries to figure out which slit the electron is going through. Now, how can you build up such a spy? You can have a light bulb placed here. And this light bulb is such that it's bathing the apparatus with light. The light is going everywhere. And if an electron, which is a particle, goes to this slit, S2, it shines. The electron shines. It reflects off light from this bulb So if you get a shine here, you will tell that the electron is passing through S2. And if you get a shine on this side, you will tell that the electron is passing through slit S3. Alright? Now if we were to perform this experiment and we would like to make an attempt of actually getting into the apparatus, installing a spy or a reporter into the system so that the path of the electron can be deciphered, which path the electron is actually taking, then what's going to happen is that there will be a shine either here or here. There's a mutual exclusivity. A shine can never happen both at S2 and S3, which means that the electron is either passing through S2 or S3. Alright. Now what we would like to do, we know that with a single electron we see interference fringes. So the electron is interfering. But we don't know the nature of this interference. What is the electron interfering with? The electron is indivisible. It can't go through both slits at the same time. So how do we explain this phenomenon? Someone comes up with the idea, okay, let's try to find out the path of the electron. Let's try to find out whether the electron is going through S2 or S3 or both. If there are shines both at S2 and S3, we'll say that the electron has indeed divided. It's divisible. And our notion that the electron is an indivisible fundamental lepton is incorrect. So we're trying to find out the nature of the electron and which path the electron is actually taking. Alright, so in order to make that observation, someone intrudes into the apparatus and installs a light bulb, a detection device, another kind of detection device that does not change the path of the electron, only observes it. That is meant not to change the path of the particle. Minimal disturbance, with minimal disturbance, it just wants to take a glance of which slit the electron is actually going through. Alright, so when this experiment is performed, this modified experiment is performed with an observer, what is observed is that the electron is indeed indivisible. It cannot be divided. It has not split into two because either S2 flashes or S3 flashes. And the electron is seen either here or here. It is not seen at both the places at the same time. And when this observation is made, the interference pattern disappears. When you put this intruder into the apparatus, the outcome of the experiment actually changes. And you don't see an interference pattern. And what you observe instead is two humps, corresponding to what happens with particles. So, this observer says that the electron is a particle. It is not behaving like a wave. There is no diffraction, there is no interference, there are no fringes whatsoever. And the electron is either going through S2, half of the time it goes through S2, there's a probability of half of taking this path and a probability of half of taking this path. And at the end, you don't observe any interference pattern, you just observe that the electrons are merely acting like particles. There is no wave nature associated with them, and there is a bimodal distribution. The electron is a particle. If you don't have this observer, the electron is behaving like a wave. So let's take a 10-minute break, and I'll take up this discussion after that. Thank you.